A co-packaged silicon photonics module sits on the bench, roughly the footprint of two stacked postage stamps sealed under a metal lid. The teardown begins the moment that lid comes off. What the outer shell suggests is a compact photonics package performing a well-understood function. What the deepest layer reveals is a design whose every internal dimension was shaped by the exact constraint it was built to escape. We work from the lid inward, the package arrangement first, then the waveguide layer, then the routing geometry that sets the loss budget at fabrication, then the electro-optic conversion point where current becomes light, and finally the copper stub, the shortest copper run in the entire stack, the one that explains every other dimension in the object. The object is a Chinese-developed co-packaged optical engine, reportedly sampling at a Shanghai Lingang facility, with back-end assembly linked to a packaging company whose primary business has been image sensor packaging, but which has been documented as expanding into high-bandwidth memory back-end integration. Every cut in this dissection returns to the same physical module. The waveguide layer, the conversion point, the stub, the ecosystem anchors are all features of this one object, not of co-packaged optics as a category. 7 cuts, outer to inner, then the caveat, then the reading. The first cut removes the lid and exposes the package arrangement. Co-packaged optics places the optical engine in the same package as the compute die rather than at the edge of the board as a pluggable transceiver module. This is the topology that companies including TSMC and Broadcom have each described in published roadmap materials as the next transition point for high-speed interconnect. The Chinese module under examination follows the same arrangement according to the company's own claims about its sampling program at the Lingang facility. No independent third-party teardown has confirmed the internal layout. The reason this arrangement exists at all is that board-edge pluggable transceivers require the electrical signal to travel the full width of the board before it reaches the optical conversion point. At data rates above roughly 800 gigabits per second per port, a threshold the industry crossed in the current generation of artificial intelligence cluster switches, that copper run becomes the dominant source of power consumption and signal degradation. Moving the optical engine into the package removes most of that run. Placing the optical engine beside the compute die rather than at the board edge is not primarily a size decision. It is a latency and power decision made visible in the physical distance, a distance measurable with a ruler, between the point where the electrical signal ends and the point where the optical signal begins. The spec sheet reports bandwidth. The teardown reports millimeters. The millimeters are the more important number. The second cut exposes the waveguide layer, the medium through which the signal now travels. Below the lid, the signal leaves the compute die as an electrical current, travels an extremely short distance, and enters a silicon waveguide where it is carried as pulses of light. The teardown suggests a run measured in hundreds of micrometers between the die's electrical output and the waveguide's input, not millimeters. Silicon photonics uses the silicon layer itself, patterned by lithography, to guide light through structures whose dimensions are on the order of the wavelength of the light being guided. This is an established fabrication technique that multiple foundries have used in production for several years. The waveguide layer exists because copper carries electrical current under physics that impose a hard ceiling. At very high frequencies, copper radiates energy as heat, and the skin effect concentrates current at the conductor's surface, increasing effective resistance. Light in a waveguide does not experience resistance in the same sense. The bottleneck was in the medium, and changing the medium was the structural move this object records at this layer. Whether the waveguide geometry in this specific module meets the loss and crosstalk figures the company claims, no independent measurement has confirmed. The third cut goes one level deeper into the waveguide layer, to the routing geometry, which is where the loss budget is set and where it is locked. Silicon waveguides in a co-packaged module are patterned during wafer fabrication. Their geometry, meaning width, height, bend radius, and coupling structures at junctions, determines the optical loss the signal accumulates as it propagates through the module. Once the module is assembled, that loss budget is fixed. A pluggable transceiver can be removed and replaced if its optical performance degrades in the field. The waveguide in a co-packaged module cannot. The co-packaged arrangement trades field replaceability for a loss figure that is baked in at fabrication and, the company's own claims suggest, lower than what a pluggable link at the same data rate would produce. That claim has not been independently confirmed. The routing geometry visible in cross-section reveals what process capability the fabrication line could deliver at the time the design was frozen. Tighter waveguide bends allow more compact routing but increase bend loss. The bend radii and the routing geometry are therefore a record of the process node, written in the silicon's geometry before any other specification is stated. For this module, the Lingang facility is the reported fabrication site. No public process node specification for the waveguide layer has been disclosed. The fourth cut reaches the electro-optic conversion point, where current becomes light and, on the receive side, where light becomes current again. The modulator, the device that impresses data onto the light carrier by varying the light's phase or amplitude in response to an electrical signal, sits at the junction between the electrical domain and the optical domain. The photodetector performs the inverse conversion. In silicon photonics, both devices can be fabricated in a process compatible with standard complementary metal oxide semiconductor equipment, though the doping profiles and layer stacks they require differ from a pure logic process. The company's own claims describe using a silicon photonics process for this module. No independent process analysis of this specific module has been published. Consider the difference between moving water through a narrow hose and through a wide pipe. Moving a very large volume through the hose requires enormous pressure, and most of the energy goes into overcoming friction at the narrow walls. Widening the pipe moves the same volume at a fraction of the pressure without changing the pump. The copper-to-light transition operates under different physics, but the structural logic is parallel. The bottleneck was in the medium, and changing the medium removed it. This is the one analogy this dissection will use. The modulator and photodetector at this junction do not require the most advanced process node available globally. They require a process node that is available. The design choices at the conversion point are not purely photonic engineering choices. They are also procurement choices, and in this object the two have become indistinguishable in the silicon. The fifth cut finds the copper stub, the residual electrical link, the shortest copper run in the stack, and the dimension that explains the shape of everything above it. The copper in a co-packaged optical module is not eliminated, it is minimized. The stub of copper between the compute die's electrical output and the modulator's input is what remains. Its length in this class of module is measured in hundreds of micrometers. The power dissipated in a resistive conductor scales with both the resistance, which scales with length, and the square of the current. Shortening this stub to the sub-millimeter range cuts its contribution to the total power budget to a small fraction of what a board-spanning copper trace would consume at the same data rate. This is established electrical engineering. The specific figures for this module's stub length and resistance are the company's own claim, unconfirmed by independent measurement. The copper stub in this module, at the dimensions the teardown suggests, is shorter than the width of a human thumbnail. The copper trace it replaces, running from a board-edge pluggable transceiver back to the switch chip, would span roughly the distance from the tip of a finger to the first knuckle. The power difference between those two lengths at current high-speed data rates is not marginal. The module's physical dimensions, including the placement of the modulator relative to the compute die's signal pads, are a direct consequence of minimizing the stub. The package is sized around the stub, not the reverse. Every outer dimension in the module traces back to a physics constraint that acts at the sub-millimeter scale. The sixth cut exposes the ecosystem layer, the production and assembly base that the module requires to exist. Reports, not independently confirmed teardowns, describe the sampling program for this class of module as operating out of the Shanghai Lingang facility, with back-end assembly work reportedly linked to a packaging company whose primary business is image sensor packaging, but which has been documented as expanding into high-bandwidth memory back-end integration. The connection between image sensor packaging capability and silicon photonics module assembly is not accidental. Both require precision alignment of optical and electrical structures at the wafer bonding or chip stacking stage. The reported high-bandwidth memory backend work at the same facility suggests an intent to pair the optical interconnect with the memory bandwidth that large-scale artificial intelligence inference requires. A co-packaged optical module does not function in isolation. The compute die it connects to, the memory stack it communicates with, and the switch fabric it feeds all constrain what the module must deliver. Whether the optical interconnect program and the memory integration program are being developed in coordination or are being assembled from separate efforts into a combined offering, the teardown cannot determine. The Lingang facility and the packaging partner are the publicly reported anchors. Their coordination is the inference, not the confirmed fact. The seventh cut is the competitive position layer, which is where this object's relationship to the programs it parallels becomes structurally readable. TSMC and Broadcom have each described co-packaged optics programs in published materials and investor communications. Intel's photonics group has shipped silicon photonics transceivers in production for several years, though in pluggable rather than co-packaged form at volume. The Chinese module enters the same transition those programs are navigating: the move from board-edge pluggable transceivers to co-packaged optical engines. It does so from a supply chain that cannot access the most advanced packaging nodes those programs use. The node gap between what is available at the Lingang facility and what the most advanced packaging processes can deliver is real and documented in publicly available semiconductor industry analyses, though the specific magnitude of that gap for photonics specific process steps is not separately quantified in public sources. This layer exists in the object because the restriction shaped it. The co-packaged approach was not the path of least resistance for a supply chain with unconstrained access to advanced packaging. It is the path that delivers the physics benefit, the shortened copper run and the lower power dissipation, while using process steps that remain accessible. The competitive position layer is not visible on the lid. It is visible in the conversion point device geometry, in the waveguide dimensions, and in the stub length, all of which reflect what the available process node can deliver, optimized to extract the maximum interconnect benefit from that constraint. Strip away the lid, trace the waveguide, measure the stub, and what remains visible at the conversion point is the following. The device geometries of the modulator and photodetector in this module are sized for a process node that is accessible, not for the most advanced node available globally. That is an engineering choice, and it is also a procurement record. The restriction that limited access to advanced lithography equipment did not prevent this object from existing. It determined the specific geometry in which it exists. Every dimension in the stack, the waveguide width, the modulator footprint, the stub length, converges on the same fact. The physics benefit of co-packaged optics can be captured at a process node that export controls have not closed. The constraint is not a gap in the design. The constraint is the design. Three things this dissection cannot settle. First, the company's own claims describe bandwidth figures and power efficiency improvements relative to pluggable transceivers at comparable data rates. No independent benchmark from a third-party laboratory has confirmed these figures for this specific module. The teardown suggests the architecture is capable of the claimed improvement. Whether the fabricated device delivers it at the stated operating conditions is a separate question the dissection cannot answer. Second, the waveguide loss budget and the modulator insertion loss, the two figures that most directly determine how much signal remains usable at the receive side, are set at fabrication and are specific to the process node and doping profile used. Neither figure has been published by the company or measured by an independent party for this module. The loss budget is the difference between a module that works at system scale and one that works only on a bench. The teardown cannot open that gap. Third, thermal management at co-packaged integration density is an unsolved problem across all co-packaged optical programs, not only this one. The modulator and the compute die generate heat in close proximity, and waveguide loss in silicon is temperature dependent. At sustained high data rates, the thermal interaction between the optical and electrical layers imposes performance limits that do not appear in room temperature bench measurements. Whether this module has addressed that interaction in its thermal design, the outer package does not reveal and the company has not disclosed. What the dissection shows is that the architecture is sound, the supply chain logic is coherent, and the physics benefit is real. What it cannot show is whether the fabricated device in sustained operation at system scale delivers the claimed figures. Those three gaps are the ones that separate a convincing sample from a shipping product. Lay all 7 cuts beside each other and a single reading emerges. This object was not designed by working backward from an unconstrained wish list of process nodes and packaging tools. It was designed by identifying the physical transition from copper to light, from board edge to co-packaged, that delivers the largest interconnect benefit, and then finding the process node at which that transition remains manufacturable given what the supply chain can reach. The restriction is not a footnote to this object. The restriction is the outline within which the object was drawn, and the outline turns out to enclose a structurally complete design, one that achieves, at an accessible node, the physics gain that the industry's leading programs are chasing at the most advanced nodes available. The gap in process capability did not foreclose the transition. It set the dimensions of the path through which the transition was made. What this module records, in waveguide widths and stub lengths and conversion point geometries, is that the boundary drawn by the restriction and the boundary drawn by the physics of copper's limits happened to fall in a place where building the thing was still possible, and that coincidence, if it holds at production volume, is the most consequential fact in the package. The next object we have been asked about is a processor built on an instruction set architecture whose license terms are, by design, irrevocable and whose specification no export control can touch. If you want that module on the table next, name it in the comments and we will open it the same way. If this kind of dissection is useful to you, the subscribe button is how you make sure the next one reaches you.